All right, hello. Thanks a lot for coming to our session. I know it's the last day and the day after the party, but we do appreciate it. My name is Greg McConnell. I'm a solutions architect with AWS, and I'm here with Zack Lydon, who is the VP of Engineering at Telltale Games. And we're going to talk about how Telltale migrated from CouchDB to DynamoDB for their story analytics. I'm going to do a really quick intro on DynamoDB. Then Zach's going to talk about, what is story analytics at Telltale. He'll talk about the early infrastructure they had, SQL and CouchDB, the migration to DynamoDB, and then finish up with how all this led to better data and better stories for them. First of all, I'm curious, how many of you are using DynamoDB for any kind of analytics at your business? A few? And how many are using another NoSQL solution? Okay, more. Cool. So a little bit of history on Telltale Games. So they are an independent developer and publisher of games. In fact, they produce, develop, and self-publish all their games, and they do so on multiple platforms: PC, console, iOS, Android, mobile. Zach's going to get into the games and kind of give you a rundown of that and even talk about the new game that was just announced last night. They were started in 2004, and since the beginning, they've been a pioneer in the genre of episodic games. So basically telling a really long-form story using chapters, individual chapters, released at different intervals, and allows them to really get deeper into the story and tell a much richer video game story. So relevant to the discussion of why Zach and his team migrated to DynamoDB is the question of why AWS built DynamoDB. And one of the reasons was that managing relational databases on your own, managing non-relational databases, NoSQL databases on your own can be difficult. I'm sure Zach would attest to that. It's difficult to engineer the performance you need when you're doing it on your own. You definitely need special expertise in a lot of cases to do this, a lot of time. And it's difficult to maintain a certain level of performance as you scale out your application. And that's really the key is, how do you maintain scale, how do you maintain performance as you scale out your application? And so that was one of the feedback we got from customers, is that doing this can be difficult. So DynamoDB is a fully managed NoSQL database. It is highly available, highly durable, because we replicate the data across 3 different facilities. It supports both document and key value data structures. It scales to any workload, and as you scale, you're able to get a consistent single-digit millisecond latency at any scale. And that's really key and important when you're considering a NoSQL database for an application that is going to be scaling very, very high. There's a number of access controls that are available with DynamoDB, including the ability to do controls at the item level. So in DynamoDB, we call rows items. And you can use fine-grained access controls to control access at the item level. And finally, there's event-driven programming, so using our Lambda function service, which allows you to upload code and then run that in response to an event. You can use that with DynamoDB, and I'll touch on that in a little bit. So again, you can get basically service-side average latency in the single-digit millisecond range, and truly that's at any scale. And there's a number of ways we do this, and like I said, this is a managed database, so this is all done for you. So one of the ways is we do use SSD drives, of course, but more importantly, we partition the data for the table for you. So as your table grows in size, and as you request additional throughput for read or write, we'll partition the data, scale out essentially, to handle that additional performance need. This is done automatically, and this is done without any impact to your access to the database. So it doesn't impact the API calls to your table. So in regards to that, you're able to specify both the read and the write capacity that you need for the table. And you can increase and decrease that. And of course, that affects your costs, so a lot of times you want to optimize it so you're getting right at the level you need and decreasing if the load goes down. But as you increase and decrease the read and write, and those are independent, basically just dials, we will then scale out the partitions as needed to maintain that performance that you're requesting. And there's really no upper limit to this because we can always scale out and add more partitions to get the performance that you need. Just a real brief view of the table structure. In a DynamoDB table, we call the rows items, and there are within an item any number of attributes. This is a schemaless database. Each item does not need to have the same attributes as another, and it's very easy to add additional attributes as needed. So it's very easy to change the table structure over time as your application changes. There's two ways of doing primary keys to uniquely identify each item. One is just a simple one. It has a partition key, and we use that partition key in a hash function in order to determine where to physically store your data across all those partitions. The other type of primary key is a composite, which is including the partition key, but we also add a sort key. And within a particular partition key space, the data is stored together, and it's stored in sorted order by that sort key. So it provides an index for you for that. And finally, there's a number of integration capabilities with DynamoDB, and it's really all based on DynamoDB streams. And DynamoDB streams is a time-sequenced order of the changes at the item level. So any puts, updates, deletes that occur to the items in a table get reported into this stream. The data is put in exactly once. It is strictly ordered. So there's a lot of interesting use cases that come out for this. It's asynchronously copied over, so it doesn't impact your original table. But using this stream, you can do a lot of things. One thing is just replicating your table to another table. So you can do that in the same region or different regions to provide high availability, high durability, a lot of options there. Another option is DynamoDB triggers. So this is kind of a simple way, easier way of doing database triggers. It's having lambda functions that react to changes in your table. And that can either trigger a write to another table or trigger off another function. There's a lot of options there, but it's basically triggers coming from changes to your tables. This is a reference architecture. It'll be available in the slide deck when we publish the talk. It just kind of shows you a number of the options that are available with DynamoDB streams and other parts where you can really have a whole ecosystem off of DynamoDB for your application. Okay, so I would like to introduce Zack Lydon. Again, he's the VP of Engineering at Telltale Games. He leads a team of engineers who build world-class tools for the development of games at Telltale. And take it off. Thank you.
Thank you.
Thanks.
Thank you, Greg. As Greg said, I'm Zack Lydon, VP of Engineering at Telltale. I've been at Telltale about 6 years. And so this topic is really kind of interesting and important to me because in our growth, this was something I actually spent a lot of time working on when I started working at Telltale, was building out our infrastructure to capture how players are playing our stories and show it back to players as well as analyze it. How many people here have actually played a Telltale game? Yay! This will be super easy to explain then. So, Telltale Games. Very briefly, I'll get into this. Like you said, we make episodic, narrative, licensed content. So we're nearly every time, I mean, with all of our games, we're working with great licenses. Lately, we had Minecraft, which is really big, Batman, and as Greg alluded to last night, we just announced Guardians of the Galaxy game next year. So this has always been a core part of what Telltale wants to be, is the best licensed game company we can, and making these great narrative games. It's kind of always been part of what the company set out to do, and now we get to work on them, and it's very exciting. The other thing about Telltale Games is that we ship everywhere. So when we make our games with our custom game engine, we're automatically deploying it to every single place we possibly can. Laptops, consoles, Mobile phones, obviously, probably a microwave at some point. We really want to get our games going everywhere possible. This is really interesting from a data side as well, because it means all the data is coming in at different rates. We support 12 different SKUs, 18 platforms, 28 stores, 10 languages, all around the world kind of being played at different rates. So getting all this data in, it comes in really, really fast, and it comes in really kind of diverse, different sessions, different time. People play offline, they go back online. So we can't have the consistency of knowing, like a web browser, we're always going to have a certain connection. So a Telltale game, like Wolf Among Us right here. So for those of you who have not played, I can kind of show you what it's like. The biggest thing you're doing in a Telltale game is you are going through stories and you're just making choices for the character. So in this case, Bigby the Wolf needs to kind of, what are you going to say as the player? And then the story reacts to you. So we're able to have the different characters going to interact differently with the main character based on the choices that you've made as a player. So when we give people choices, we give them, usually we want to give them choices that make a meaningful impact to how they're experiencing the story, as well as, allow the story to kind of react in ways that they would expect. So if you're kind of nice or you're mean or kind of however you're playing your version of that character, the world will actually react to it. And we've done this locally for a long time in the data itself. That is kind of what the game engine does, is we have, we're able to, track what players did earlier, look back at that data, and then show them while in the middle of gameplay how the world's going to react differently to them. So when we started to bring it online about 5 years ago and start to track that data kind of globally, that was kind of the fun part of actually seeing how everyone played these games in aggregate, not just our own little tests. So users make these choices. We basically just track them all as IDs. So that means everything is a giant unified JSON event log. So if you play a Telltale game, basically what we're doing is we are just tracking every single thing a player ever touches. So for us, that means that a given episode probably has maybe 2,000 choices in it, I would say. Over the course of a season, sometimes it can be maybe 11,000 choices. Some of these, if you guys have played a Telltale game, there obviously aren't 2,000 choices you're making in a game. There's probably about 150. But there's a bunch of other interactions you're making all the time, whether or not you're going to look at a certain item first, whether or not you're going to, go and examine parts of the world. There's easily 2,000 lines of dialogue written for a Telltale game. So when I say a node, I kind of mean anything you're interacting with in the world, any way that the character is actually doing something in the game, that's going to be tracked. With the millions of users, it means we have a lot of events coming in. About 21 terabytes of events are currently stored, and we're right now parsing at least 1 million of these play sessions every single day. The other thing about the data is it is very, very spiky. So we have, huge spikes when we have new episode releases because obviously, particularly when they're timed with things like the Walking Dead show coming back or things like that, it can end up being really, really high volume. Interestingly enough, 5 years ago when we actually started with this, and I'll kind of talk about what our early infrastructure was, we really did not know what it was to store thousands of nodes, and so we had a situation on our very first launch of Walking Dead where we basically released the game, hits the Xbox, everyone starts playing it, and our servers crash instantly because we just had so much data coming in at such a high volume that we could not even expect it. Luckily, we were able to fix that and get it working, but it was definitely scary when we didn't quite understand what it meant to be storing, maybe 30K of data for every user that's uploading every 5 to 10 minutes to us. So choice data, when we get all this, what do we do with it? Well, the really obvious thing we do with it that everyone sees, and really its original reason we did all this, was just to show players how each other are playing the game. So, if you've played any Telltale game, we always show this at the end since Walking Dead, which is where first implemented this on the platform, is just us grabbing what we think as developers are the important choices in the game, then having the documents come in from the players, aggregating all of those, and then sending it back down to the user so that they're able to see what the actual choices are and to see how they compare. So that you can look and understand that you're in the 12% of people that maybe made this important choice for a character, you're in the 80% content that are going a certain direction. It's kind of however we want to do that. So this was really the only reason we built the entire infrastructure, was to show this screen at the end, which is pretty cool because it doesn't seem like a big deal at the time, but it was one of the things with Walking Dead in particular that I think made players start to talk about our games in kind of a wider context and start to really look that these choices are kind of hard, that the game, while maybe not having like massive branching, certainly reacts to you differently. People go through the game and feel very different about the world, and now they can see kind of how everyone did that. The other thing we do with the data that people probably don't see as much is we do a lot of heat map evaluations of how players actually go through our games. And we do this is not our tool, but you can kind of imagine a Telltale game is a giant node graph, right? If you're going through and doing all the little choices. We're able to use that, grab all the data we've aggregated, feed it exactly back into the same tool that the designers and writers are using to build the game, and then they can kind of look at an interactive heat map of how users are playing their game. So with this, we're able to actually evaluate how good is a choice? How interested are players in this particular path? If we see that 3% of players have gone down a certain branch, then we know that maybe players weren't that interested in that. Let's analyze that. Let's look at why that was a good choice or a bad choice, or which line people chose. Using this data that we've done, we've done this more in the last 2 or 3 years, really kind of allows us to alter the stories on the fly, which I think is something about being episodic that we have always done, is that we develop games live. So we do not make 5 episodes and then release them slowly. When episode 1 is out in the market, episode 2 is still being developed. Episode 3 is still being developed. And so we've always had that. And before we did this heat map technology, we would also kind of just do the regular things. You read review articles. You talk to influencers in the community. We figure out what people think about our games, but it was very kind of unobjective. Once we were able to actually grab the data, we knew very objectively how people were playing our games, because we could look and actually see the data and know this is stuff people want, this is what they don't want, and it really improves our games going down the line. Every episode is able to use that to then get more. And it allows us, doing that, to really personalize the stories. So that is where we are not spending our time on paths that players are not that interested in. We want to spend our time on the ones that are 50-50, that are really tough choices that users are actually interested in. And by aggregating and looking at the data, we're able to kind of deliver that without kind of in a very kind of raw way. So now to get to the infrastructure of what we built and then how we transferred over to Dynamo, now that everyone kind of understands a little bit about what Telltale data analytics are. We also do other analytics too. It's not just this, that's just the cool stuff. The logs end up storing everything that we ever want to track like any other company, but this is the stuff I think is kind of neat. So really early on, this is 5 or 6 years ago, we're like, great, we want to do this project where we're storing all the data. We're like, how do we do this? Well, our server guys say SQL, we can do this. We're like, no, that's impossible. So it was no way that we're going to handle that on scaling. We didn't have the amount of data we wanted to collect was going to come in too fast. It was going to just blow up. So we're like, no way. We kind of killed off that right away. And we started to look at what other options we had. Obviously, NoSQL databases seemed to be perfect for what we wanted to do, particularly because we wanted to store things as these kind of raw, just kind of dumps of the JSON player sessions. So this is where we started with Apache CouchDB. So basically, we went to the solution first where we're going to have everything. It was very manual. We had to kind of spin up our own servers on this. There was a lot of node failures. Like I said, the data comes in really, really messy. And so we had a lot of time where we would have different things failing and have to go and kind of bring them back up and bring them offline. It was becoming a real serious problem. As well as once we started to get a bunch of users from around the world, we would hit document limits on the individual servers and end up having to have things across multiple ones, and it became very, very difficult for us to actually maintain scaling. And at the time, ended up having really 2 people full-time just keeping this thing running as often, just kind of keeping it all kind of going together. As I said, like initially this was a very tough, challenging thing for us to get going because of the amount of data coming in, because of how spiky it is. Weekends would come in and it would just kind of immediately blow up for us. And that's just kind of in the raw, get the data in, aggregate it a little bit, and then show it back out. The second problem and the second kind of big issue we had was processing this data. So doing these things like these heat map evaluations and, basically we had a bunch of data that was stored, but at the time we were storing it, we didn't even have that sort of technology to look back at the data. We weren't 100% sure how we wanted to use the data. Where were users gonna, how are we gonna actually use the data to do this? We just wanted to store it. So because of that, we basically kind of backed ourselves into a corner where it was nearly impossible to actually process things at any relatively real speeds, just because of the nature of how we stored the data wasn't exactly formulated because we didn't know. The only thing we knew we wanted to do was the aggregation. So basically that meant all we were doing was that, and not instead of some of the newer stuff we're doing where we're actually capable of analyzing the data in new and interesting ways, which I'm going to cover kind of at the very end, but none of that was even on the radar because of just how hard it was to do this. Also, part of that was, we would have to kind of manually scale up to handle the incoming bulk load. But if we did want to, say, run a really particular query, there was an episode that we really wanted to know information about. How did users feel about this or that? And we wanted to run a deeper analysis of how many players did this choice and this one, or anything like that. It just kind of became impractical. So we kind of gave up on it because the data was not available to do that. So this is where we kind of decided we need to move on from this and find something that's going to not take us so much time to maintain and is going to allow us to have the ability to process data in maybe ways we didn't fully expect to do it. So this is where we decided we would want to try migrating to DynamoDB. Yay. So moving over, we immediately kind of ended some of our maintenance. As we said, it's fully managed, so we didn't have to kind of spend all the time doing that. Storage limitations were really big for us. 200 billion event peak is pretty much where we're kind of get. We get about 10 gigabytes of data coming in a day on these event storage. So this is something, without having that, we would really have no way of getting that going. The data was coming in so fast that it's just impossible for us to actually do that. Right now, we have about 1 million session uploads per day under a second response time because we're able to scale and adjust to all those spikes. We start at 50 read writes per second, but it could go up to 20,000 writes spikes in some of our days. And currently, we use dynamic DynamoDB in order to auto-scale for this so that we don't have to kind of go in there and manually actually adjust it. So this was really kind of a lot better for us than what we had before where we were spending a bunch of time doing it. Now our server engineers are more kind of writing the processing and everything else as opposed to just trying to keep the data kind of flowing and going. So this is kind of our general, view of our server. So it's pretty standard here, I think. Gives us our high throughput, scales elastically, caching, CDN use extensively. This is kind of just our common backend. But you can see, for us, it's you can see we have the data coming in from the game clients for the event logs, but there's also a lot of other data traffic that we're going to send through them, like patches. We feed our own DLC. We do our own data packs on many of our platforms, so we're constantly needing to not just grab incoming session data and analyze it, but also, prepare patches for platforms, send documents on when new episode availability is there, feed strings, all of that sort of stuff. We can also kind of flow back to the user once we've actually got it. So processing. So now we have basically separate tables per game for independent processing. That was another issue we had before, was we kind of got everything from every game all together and used keys inside of it to figure out which one it was, which obviously led to some very noisy data when data kind of formulated slightly differently between games. Now we just kind of have separate games tables for every game, and then each of those is going to be able to kind of independently process what we need for each of those. When we're processing now as well, we're only reading just the data we need for the query. This was a big problem we had before where in order to get at some of the data that was stored, we would basically have to go through and grab a ton of it out, search it, find the data we wanted, and then that process would take a really long time. Now we're able to kind of just only get the stuff we want because we've set up the keys so we have that. Right now, we also export the entire tables to S3 in about 24 hours. We have no loss, so we're also kind of getting rid of this problem we had of kind of data corruption and loss. And the part I like is we're able to adjust to new queries really quickly. And that was something that I think was kind of mission critical for us going forward, because that's how we want to find new ways to get at the data so that we can kind of give users better experiences. So in terms of costs, we basically went from one server was handling literally what 12 did before. So it was just a huge reduction now that we were no longer paying for a bunch of static machines that were kind of storing the data because we might want to process it, or that was taking a long time to get it, that it's going to be there. We're really roughly about the equivalent cost to when we started. However, our load since our original Walking Dead game is at least 10 times higher. So we're able to basically keep costs pretty fixed throughout, but we've managed to handle just an incredibly more load, particularly with Minecraft, which is a pretty big and popular game. And we're kind of only reading kind of the exact data that we need at any given time, not kind of all of the, not kind of trying to pull it all out. So challenges, improvements. So yeah, I mean, in general, the transition actually went pretty smooth, as a lot of my previous slides had mentioned. It was not too much trouble once we kind of built out the architecture. One of our bigger issues was that we still have a lot of data that was kind of mixed between the two systems, and so we had some data we could only pull from the new one. We had to go back and pull a lot from Couch. That kind of continues to be somewhat of a maintenance issue, though nowadays I think if we want something, we just try to pull it all over into the new system so that we're able to process it in the same way that we process everything else. Integrated rewrite provisioning would be great. That was one of the things we thought would be, we obviously use the script to handle it now, but if that was integrated in, it would be one less thing we'd have to handle. So that was one of the ones that I think would be pretty useful as well. So yeah, that's our kind of transition to why we went, how we went from Couch over to DynamoDB. So one of the things I want to talk about here at the end is what's some of the stuff we're able to do with this now that we have it over and are able to run analysis that kind of like I was alluding to that we weren't able to run before because we just didn't have the, we weren't able to process the data at any real speed, so we couldn't kind of come up with creative new ways to look at how people play a Telltale game. So in some ways you can look at our games as, they're kind of, big personality tests or anything, right? Where players are playing, making these hard choices. They're really interesting choices. So what we wanted to do was, how can we better understand how players are playing our games? When we build them, we do sit and think about, are players going to be, you want to give players some options to be certain types of characters, right? But in a huge, big, giant game, there's only so many of those you can maintain. So while we of course go through and you want to be an aggressive big B, you want to be, particularly here with a Batman game, how much you lean on Batman versus how much you lean on Bruce Wayne. Those are obvious, kind of story rails that you can go with. But at the same time, there's a lot more subtlety to that. And so we kind of had the question ourselves of, are players on their own, creating their own ways that they play through our game? So, we wanted to know, as opposed to, right, kind of where we started, where we ask really specific questions because we believe this is how players want to play our games. We choose the choices at the end we think are important. We wanted to kind of do it in reverse and be like, what if we don't look at the data in terms of what the actual questions and choices are? What if we just let the data instead speak to us and tell us how users are playing our games and how the choices are actually becoming important? So this is where we wanted to kind of understand player behavior more than just our regular aggregating data, knowing what lines are working, personalizing to audiences, which are all the things that we've been doing previously. We wanted to kind of do some other stuff. So this is where we started to use our fun data scientists to go and look at Playstyle clustering. So basically, as I said, all of our games, all the choices we make are just raw IDs. So we're able to take all of that data and try to ask ourselves, how are users on their own grouping and going through the Telltale games? So we used a k-means clustering, so trying to basically find, of players, how many were very close to each other in the choices they were making, and also far from other people. So that's what what the algorithm is kind of meant to do, is try to find where players are naturally aggregating and making similar choices to each other that are distinct from other players. And if you can take that data and look at, which of these clusters, when you have people that play very similar play styles, what sort of choices are differentiating them from the other clusters of play styles. And again, this is purely from a data side. We did not actually try to say, how close are they to an aggressive play style or to a nice play style or anything like that. We instead just said, let's just let the data gather people together and see what we can infer out of that when the data shows us which choices are actually important. And then can we use that to identify what sort of player personas are actually out there instead of us trying to kind of guess at what we thought players would be doing. So we ran this data. It was pretty cool. We ended up getting, I think, 23 different clusters of people, though in reality there was only I think there was only 8 of them that were, that made up the 85 or 90% of the actual people in the analysis. As you can see on our model selection, we kind of were able to, look at all the nodes there, group the ones that were very similar together. The column in the middle is actually bringing the data back to then looking at the choices. So we were able to then go and say, if there was a group here, what made it unique was that it made these 2 or 3 critical choices. And basically, every choice in a Telltale game we could list out as its kind of importance relative to other choices because it helped distinguish clusters of players together. And this was really cool because we found out that sometimes choices that we thought were really major didn't end up being that major to people in terms of differentiating how they played the game. They ended up being that most players end up choosing this one path or, half and half, or it was something that wasn't very distinct, whereas there were a lot of other kind of more subtle choices that were made in the game that really distinguished playstyles quite a bit. So then we were able to go through and grab all of those choices and then look at them back in context. So if we found that, the 15 choices that really seemed to differentiate how people play through the game, we could then make some judgments based on each of those groups and what they chose, what type of player they were. So we did this again, and we came up with some kind of these little buckets of play. We ran this on Walking Dead Season 2 because that was kind of our best, latest DynamoDB data. So this is where we were able to come up and say, this group, we call them amoral and ambivalent. It was the second biggest cluster. We had 22% of our players. And they basically made a bunch of these choices that were, set up there to kind of be very kind of independent, very value-driven. Like in this one, they befriended Jane. Nick died at the ski lodge. They decided to rob them. They kind of made a bunch of decisions that were, kind of amoral, but represented a really big version of how people play through The Walking Dead. So this data is kind of neat for that reason because we're able to, let that data kind of come out of it, and as opposed to kind of guessing that we'd have amoral and ambivalent players. We actually do some of this analysis on our own ahead of games anyway, where we kind of decide what sort of places we're gonna do it. But now for Walking Dead Season 3, which comes out pretty soon, it's the first time where we're able to build that game using knowledge of the actual styles of play that people go through Telltale Games, as opposed to what we kind of figured they were going to do. Another one, My Best Self, was another one of our clusters. Very logical, very reasonable players. They made a lot of kind of comfort, like a lot of decisions to kind of be a kind of a good person in an ugly world, things like this. And basically we could deliver these to our designers, these 8. This is the style of how people are playing through your Walking Dead game. And able to give that to them, and they actually, were able to use this in the next upcoming version of Walking Dead to ahead of time start to build choices in that we know we're going to lean to the type of ways that people are playing our games. I think this is really fascinating, not just for Telltale, where we're making these choices games, but I think because in particular we're working on so many cool licensed narrative games, it tells us a lot about the license itself. So for Walking Dead, where we've been in this business making these games for a long time, it's great that we know exactly what sort of stuff the players are going to go through in it. Cool. And that is my presentation.